with respect to the numbers of either sign. If you have a negative number and you turn it into an absolute number, it can only be turned back into a negative number, never into a positive number. The absolute has to do is of course, the quantity of that number, regardless of which sign it is. That is a big difference. There's also a difference in symbolization with regard to addition and subtraction, but I won't mention that here. Now, chapter 5 shows the harmony which exists within the imaginary system when two incompatible numbers are associated. The imaginary system number is not a conjunction, but an association in which the repetitions of the variable number, square root of minus 1, supply the base, and the real number provides the coefficients. An imaginary axis is a stack of square root of minus 1 separated by a real 0. The count of the stack, whether plus or minus, is in real numbers. They're able to work together by being separate. It is the movement of a radius vector which supplies the unity. Chapter 6 performs the act of synthesis which corresponds to the analysis of the previous chapter. And basically, I just begin with lines and construct the whole thing from the bottom up. Appendix A, which appears after the final chapter, shows how the imaginary system can be improved by being made completely circular. Chapter 7 compares and contrasts the veritable with the real number system. It begins with a discussion of the number line as an indispensable prerequisite for understanding numbers. It continues with a discussion of how the two-sign number systems are modifications of the absolute number system, which is simply numbers without signs. It emphasizes the different ways that the two-sign number systems handle the concept of direction. How the negative sign in the real system is used to mean both subtraction and direction, whereas in the veritable system, that sign is used to mean direction and nothing but direction. This chapter shows two important meanings of 0. The first is 0 is a point of neutrality in the number line. It is an infinitesimal and therefore has some being. The second is utter 0, which is symbolized by a much heavier 0, and means the total absence of being. The discrimination between the two is essential to the veritable, but not to the real. By failing to be fully cognizant of the two kinds of 0, the real system divides into the wrong 0. It's very important. This distinction between those two zeros is unnecessary in the real system. And in fact, as you know, is hardly noticed at all. There's a third 0 too, and the placement 0 that's used in the decimal system. But it is, really compatible, can be used with either one. And there are other zeros as well that aren't mentioned in my book. For example, sometimes you'll see an elevator where the main floor is just called the lobby, and then the next floor is called 1. Once in a while you see that. So there are other uses of 0 besides the 3 I named, but that is the only use. Those 3 are the only ones used in my book. Now, chapter 8 discusses negative roots and numbers. The variable system can handle negative roots for rectilinear as well as rotary uses. Like the real, it uses, however, the imaginary system is strictly rotary. It reminds me, as I pointed out in my book, of that Newton string, the waltzing mouse that can only go around and around. Like the real, it uses the square root sign. Well, I won't talk about symbols here. It also, the representation of the fractional exponent is the same. The powers of the number are symbolized the same. The differences show up in the symbolization of real negative numbers, which are handled in a manner exclusively reserved for positive numbers in the other number system. When the status of negative exponents is fraught with controversy in the real system, Its handling is straightforward in the veritable system. Inverses in the veritable system are symbolized by a type of italic I. The veritable inverse is more precise than the real, and circumstances exist where that is to an advantage. While a number to the zero power, a to the zero, equals 1 in the real system, plus or minus a to the zero can equal either plus 1 or minus 1 in the variable system, depending upon the sign of a. Now, chapter 9 shows how the variable system handles logarithms. The explanation is needed because the range between plus 1 and minus 1 in plus or minus a to the zero power equals plus or minus 1 cannot be treated in the variable system exactly the same way as in the real system. The answer is that subtraction can take place within an axis without changing signs, without crossing the zero of neutrality. This I call a veritable deficit. The chapter, and this is very important because it answers the problem posed by logarithms. You do not go over to the other. If you're in the negative, in the positive, you do not go over to the negative. You can stay within the negative. It's just a subtraction. It is a deficit, and it works just fine. I use a standard logarithmic problem from the textbook, and which consists of two numbers multiplied by each other, divided by a third, and do it 3 different ways, so it shows how this works out. Okay. Chapter 10 explains how the veritable understanding of deficit negates any superiority which might be claimed for the real system, owing to the latter's recourse to the principle of reflectivity. This chapter also shows how the real number system computes both subtraction and direction on the one hand, and utter zero and zero neutrality on the other. This chapter also introduces the variable surplus, which is the opposite of the deficit. Chapter 11 shows how the variable system handles fractions with mixed signs like plus 4 over minus 4 far better than does the real system. The real number answer that the quotient must be negative actually runs against the standard definition of a fraction as part of a whole and replaces it with a variant tinged with a positivistic meaning. It also subtly makes division an appendage to multiplication. Chapter 12 shows how the variable system handles Cartesian coordinates better than does its real rival. The signature of the first quadrant is clearly distinguished from that of the third. Now, you know that in the standard Cartesian, the first quadrant is plus plus, the third quadrant is minus minus, and this third quadrant is also treated as a plus. In the variable system, it's minus minus. It remains that. And also the second quadrant from the third is distinguished because in the second quadrant, in the real system, you have plus minus, and in the fourth minus plus. But they're both called minus. In other words, they're indistinguishable. In the variable system, they retain their identity. So you know at every point which quadrant something is in. It never fools you. Chapter 13 shows how easily the variable system handles polar coordinates. It also tells why the curvilinear signs cannot be reduced to rectilinear signs. That the symbols of the former, which is a plus inside a zero and a minus inside a zero, cannot be equated with plus and minus. Tabulations of the two sets of sign are taken for tangents, cotangents, secants, and cosecants. Chapter 14 shows how the variable system can handle certain types of calculus derivatives which the real system must skip. It also solves the apparent difficulty raised by trigonometric